Hey, what's up, HVAC Control Pro? If you're like the rest of us, you have your customers asking, how can I save money? How can I save energy? One of my favorite products of all time is the Belimo Energy Valve. It solves a myriad of problems. That's just a fancy word for meaning a lot of problems. But the bottom line is it saves energy. And there's a technical term for it called low delta T. It basically means that most systems are oversized and we're putting more water into coils than we need to. The Belimo Energy Valve solves this problem. And hey, to find out specifically how, I'm reaching out to my friend John Hildebrand at Belimo. John, explain to people about low delta T and why that's important.
Low delta T syndrome is a common problem experienced in buildings around the world. It has a great impact on operating expenses as well as on the environment. My name is John Hildebrand, and I'm with the strategy and brand management team at Belimo. Scenes like you see in this picture are becoming much more common across the world. As climate changes, the world dries up and gets hotter. CO2 gases emitted into the ozone are causing temperatures to rise in drastic measures. The Paris Agreement was signed by 170 countries to address this problem. They're looking to curb CO2 emissions and reduce the impact on the global warming situation. Buildings are an integral part of this ability to lower CO2 emissions. They're a huge part of the global energy system. Buildings use about 40% of all global energy, about 25% of all water is used by buildings, and 40% of all natural resources are absorbed and used in buildings. They also emit about 1/3 of all greenhouse gases, which is attributed to the increase in global temperature.
Studies show that if you tap a coworker on the shoulder with a question, it takes 23 minutes to get back to full concentration. It's time to say no.
For buildings to be able to realize their potential, they must become more energy efficient. According to LEED, about 33 to 39% of all energy is used in the HVAC system. Green Building also estimates that about 6% of all global energy use is consumed in cooling buildings. As discovered in the Helsinki report, buildings with central plants are far from energy efficient. They suffer from a problem called low delta T syndrome. Research also suggests that almost half of all buildings in the world at some point suffer from a low delta T condition. We can see there's becoming a very high awareness of low delta T syndrome. We can take a quick look at Google searches and we can see in less than half a second we can see almost 1.2 million results in people searching for evidence or solutions for low delta T. So you might ask, what is low delta T syndrome? Low delta T syndrome is a phenomenon found in buildings when we pump too much water through them, more water than they're actually capable of using for energy. These conditions can arise from a multitude of different ways. The first way is when the coils and the valves are oversized. This happens quite a lot because we size valves for a condition that would take in the worst case scenario, the highest temperature condition or the largest load. They have to be capable of working in that condition. But what we realize is that 80 to 90% of the time, valves don't see that much flow. They work in a much lower operating load. We also deliver too much water to these valves. Coils also can degrade and foul and scale as they age. This minimizes their ability to consume and use energy properly. And finally, we don't dynamically balance systems. We typically balance the water system at a maximum load, and we don't balance it for the loads that most buildings operate on at most of the time. To give you the full effect of low delta T syndrome on a building, we're going to step into my classroom and I'm going to give you a quick lesson on the power output. So we're going to use a formula for power output. And this formula, as you can see here, states that for a given constant load on the coil, flow and delta T are inversely proportional. The power output is in BTUs, and we use the flow times the delta T to come up with our load. Once again, it's important to remember as flow goes up, the delta T goes down. You can see on the graph, we have our power listed in BTUs along the left, our flow along the bottom axis in GPM, and then our differential temperature on the right axis. You can see on this line our power curve. As our flow goes up, the power through our coil increases. At the same time, just like we showed in our formula, as our flow is increasing, the delta T line, the blue dots, are continuing to fall. That is the inverse relationship between flow and delta T. What happens to our coil when the coil receives more flow than is needed? You can see on this actual chart, we do find a point on our graph where our power curve begins to flatten, and then as you can see, actually seems to decrease. Above that, the delta T line continues to drop. We can chart that point on a graph, and we call anything beyond that point, any flow beyond that point, the saturation zone. The saturation zone includes a few characteristics. We're pumping more water than we actually need for the power that's demanded. We're reducing the delta T far below design, and we're not adding any additional energy to the system. There's no more kW or BTUs available in that coil. There's a cost in entering this zone that can be displayed also on this same graph. What I'll show you is 2 points along the power curve, which represent the beginning and into the saturation zone. We'll pick these here. The first one is at a flow of 55 GPM. The second one is at a flow of 65 GPM, where you can see our line has already flattened out. What does this mean in actual pumping energy? We can use a formula called the pump affinity law to determine how much this additional flow or this additional use of energy actually costs us in pumping horsepower. We can take those points from our chart and we can add them to our formula you can see here. With this, we can see the additional pumping requirements required. As you can see on this chart, for the rise in BTUs of 5,000, which is a very nominal gain in energy, 1.6%, we're using 16% more flow, and we're pumping 65% more pumping energy for that very minimal gain in flow. This is a low delta T condition. A huge increase in pumping to a very small increase in energy. We've now seen how low delta T can waste energy at the coil, but it can also have a dramatic effect at the chiller plant. At the chiller plant, flow and delta T are inversely proportional, the same as at the coil. Once again, as flow rises, our delta T drops. We can use a formula for chiller capacity and chiller usage, as you see behind me. We'll use GPM and tons divided by the delta T will give us our chiller capacity. For example, if we have a chiller designed for a delta T of 12, a 500-ton chiller will run at 100% of its capacity. This is an efficient arrangement of a chiller, one chiller using its maximum efficiency. For example, if our delta T in our system operated at an 8-degree differential temperature instead of 12, we would require 1,500 gallons per minute to reach the same load condition. Because of this, we will need to bring a second 500-ton chiller on board to use the extra capacity of flow. This chiller needs to come on board not because of a temperature change, but because we're flowing too much water in the system. So you can see a delta T drop or an inefficient delta T results in us having to run extra equipment, chillers, pumps, condensers, things that we would not normally have to run. From this, we found that if delta T could be maintained at its design level, a central plant could operate much more efficiently. We have such a product at Belimo. It's called the Belimo Energy Valve. The Belimo Energy Valve has been used very successfully in the past in controlling delta T with some very interesting clients. The first one that we have is the Massachusetts Institute of Technology. They had a delta T problem in their Hayden library. We installed Belimo Energy Valves on the library, and we were able to raise their delta T from 6 degrees Fahrenheit to 12 degrees Fahrenheit. This reduced their chill water flow by 49%. It was found by an independent third-party auditor that if they were able to experience this delta T change throughout their campus, their energy savings would be about $1.5 million per year. In Southeast Asia, we have the Nanyang Technical Institute. As you can see, their peak water flow through the chilled water coil is reduced from 25 liters per second to 18 liters per second. This was an 18.4 reduction in average daytime flow. This resulted in quite a huge energy savings in pumping energy. And finally, the Hillside College in Mossy, their delta T was raised on an average of over 3.5 degrees Fahrenheit, and they reduced their chiller usage by 300 hours per year. This also resulted in a 16% reduction in their energy consumption, all by installing Energy Valve. The Energy Valve has been recognized across the HVAC industry as an innovative and powerful solution, particularly for low delta T syndrome. What we've learned is to achieve a higher energy efficiency in buildings, a change of mindset is needed. A building revolution is needed to meet the requirements of the Paris Agreement and the Helsinki Report. Closing the performance gap in buildings will lead to better energy efficiency and better energy usage.
Okay, man, there you go, HVAC Control Pro. Belimo Energy Valve, a really cool product. You can get that through pretty much any Belimo distributor across the country. Some of my favorites, a group Stromquist and Company is a member of called CGNA. I'll put a link in the video notes for this. But if you're having trouble finding it, consider maybe buying from my favorite distributor, Stromquist and Company, based in Atlanta and Orlando, Florida, stromquist.com. We'll see you next time, Pro.